Hello, everyone, and welcome to our talk. I hope you enjoyed the keynote in this morning, and that I also hope that many of you saw our roadmap session. And now let's dive a little deeper into graphics. I'm Oliver Schnabel, Technical Product Manager at Unity in the graphics team. I work out of Germany, and I'm focusing on the rendering pipelines and also the framework around it. And now I would hand it over to Damian, who's going to do the first part of the presentation.
Hello, and I'm Damian. I'm the product manager for platform graphics at Unity, so looking over lower-level graphics APIs, ray tracing, and so on. And in this session, we'll talk about the latest optimizations to rendering performance in Unity 6. With Unity 6, we introduced a range of optimizations across different parts of the graphics pipeline. From the render loop, compute, pixel processing, ray tracing, different optimizations address different bottlenecks. And to improve our game's performance, we should first understand our bottlenecks. To do this, we recommend you use the rendering debugger, which allows you to very easily track the CPU and GPU latency of your rendering, as well as the latency of specific passes and effects. In this example here on the right, we see that most frame time is spent on the CPU. And rendering debugger tells us that we are fully CPU bound, so we may want to reduce our CPU overhead. In this example, we're rendering the same content, but using the high-definition render pipeline at 4K resolution. And we'll see that the GPU latency increased significantly, that we are now GPU bound. And we'll also see that pixel post-processing is taking the longest compared to other passes on the GPU. So in this case, we may want to go to the post-processing settings and try to optimize those. To reach a high frame rate, we only have a very short amount of time to render and present each frame. So for 60 FPS, only around 16.6 milliseconds. So every millisecond counts. We also recommend you use the editor's profiler, which allows you to track the rendering latency. In this case, we see that the main thread on the top and render thread on the bottom both spend a long time processing the render loop every frame. And if we could actually reduce this latency, we'll increase our frame rate. Now, to learn more about profiling with Unity, I recommend you attend tomorrow's session, where Peter Hall will discuss how to boost game performance with the various profiling tools. But here we'll mostly focus on graphics. And we'll start by a bunch of optimizations to CPU performance. On modern graphics APIs like DX12 and Vulkan, we can record our command buffers, or graphics commands, over multiple threads and submit them to the GPU much faster. And with Unity, we support this via the graphics jobs mode, the system. And we introduced a new split jobs threading mode to improve performance by reducing the synchronization between the main thread and the graphics job threads. And this is supported now on DX12, Vulkan, and compatible console graphics APIs, with more platforms to come. You can very quickly select your preferred threading mode in the player settings between native, legacy, and the new split jobs mode, which is now used by default. And here on the right side, we compare the different threading modes. We see that with split jobs on the 3D sample project, we increase our frame rate by around 33% compared to the older native jobs mode. And we also introduced graphics job support in the editor for DX12 to be able to multi-thread the scene and game view rendering in the editor. In this case, we're testing pickpox into the dead or darkest days. We saw that in the editor, with split jobs, we reduced main thread latency by around 7 milliseconds and render thread latency by 4 milliseconds. Next up, we'll discuss another common cause for rendering bottlenecks, specifically stutters, and that is runtime shader compilation. This happens whenever we render new materials, shader variants, for the first time as we explore our scene. And traditionally, we address this using a function called shader warmup, which basically just pre-cooked or warmed all the shaders before loading the scene. But on modern graphics APIs, like Vulkan or DX12, runtime shader compilation happens as part of PSO, or Pipeline State Object Creation, which in addition to the shader program requires additional graphic states, which can be determined at runtime, like vertex inputs, rasterization, settings, and so on. So to support this, we introduced the graphic state collection API, which is actually quite simple. We can very easily just trace the PSOs that are created at runtime, saving them to a collection, to disk. You can then load these collections at runtime and perform on-demand PSO pre-cooking or warm-up. And the warm-up function will now return a job handle, so we can pre-cook PSOs asynchronously in the game's background. In this case, we're testing the API using the 3D sample project again. We see on the right side, we have a fly-through of the scene without PSO caching, and we'll notice stuttering and freezes, like right now, when we enter a new part of the scene. On the left side, we simply just pre-cooked the PSOs before loading the scene, so we get no stutters, we get a smoother fly-through with a much lower maximum frame time. And to cover additional optimizations to the render loop, hand it back to Oliver.
Yeah, thanks, Damian. So now let's look at the render loop optimizations. With our SRPs, we have multiple optimizations to reduce the CPU time that Unity requires to prepare and dispatch the draw calls. Set pass calls are required to prepare material data and shaders before any object can be drawn on the screen. This is the moment when Unity needs to configure the GPU with the correct shader, textures, and other state information. This process is slow, so binding resources to the GPU is a high overhead operation, especially as the complexity of your scene increases. This is why it's so important to have an eye on the stats window here and look at the set pass calls. Each unique combinations of materials, textures, and shaders results in additional state changes. The SRP batcher can significantly reduce the number of set pass calls. Instead of resending material data for each draw call, the SRP batcher allows material data to persist on GPU memory, reducing the need for constant updates. And this reduces the amount of resource binding and updates needed between drawing commands. And as a result, there's a significant reduction in CPU overhead, especially in scenes with lots of materials and objects. And next, we also have the Batch Render Group API. And this API allows you to generate draw commands more efficiently using burst jobs to optimize performance. And by leveraging burst jobs, you can generate rendering commands in a highly parallel, optimized way, significantly speeding up the processing on the CPU side. It stores custom per-instance data in persistent GPU buffer, which means fewer updates to the GPU resources, reducing the overhead of sending data for each frame. The Batch Render Group API is fully compatible with SRP shaders, ensuring seamless integration with Unity's modern rendering pipelines. And the Batch Render Group API is also fully supported across all major mobile platforms with OpenGLES, Vulkan, and Metal. This allows you to create richer scenes and higher visual fidelity on mobile devices without compromising performance. The Megacity Metro demo showcases large-scale streaming and rendering using the Batch Render Group API to handle the complex environment efficiently. Vulkan also allows us to more efficient resource management and reduced CPU overhead, resulting in better frame rates, as you see in the video. The demo uses URP, ensuring great visuals while maintaining high performance across all platforms. The system can handle 128 players on both mobile and desktop platforms, showing how we can achieve scalable, high-performance gameplay even in massive environments. Make sure to check out the demo yourself at the expo floor and maybe play it on yourself. And in the demo, as I said, we leverage the BRG API along with Vulkan's shader storage buffers to manage rendering more efficiently. And by using shader storage buffers, we can dramatically increase the number of instances per draw call, reducing the overall API overhead. And this means the same amount of work is being handled with far fewer CPU to GPU interactions. And Vulkan's support for the VFX graph system on mobile allows us to simulate complex particle effects directly on the GPU using compute shaders. And this offloads heavy processing from the CPU. Vulkan also enables specifying draw parameters indirectly on the GPU, allowing to be more flexible and have a more efficient rendering. And on average, we have seen a reduction of 972 draw calls, highlighting the significant impact of the BRG and Vulkan together in this megacity metro demo. Here we can see again like a direct comparison between Vulkan and OpenGLES performance, and it's based on CPU on the left and FPS changes on the right. The first chart shows us the average CPU time in millisecond, and with Vulkan we observe an improvement of around 5 milliseconds on average. This means Vulkan is much more efficient at handling the rendering pipeline, leading to reduced CPU overhead. The boost in the frame rate you see on the right also demonstrates how Vulkan improves the overall performance and responsiveness of the game. In this scenario, we kept the frame rate to simulate a real-world mobile gaming experience. And the goal is to ensure stable performance over an extended period. One key aspect to highlight here is the thermal performance. Vulkan's lower CPU overhead means that the device stays cooler over time, as it uses less power to perform the same task compared to OpenGLES. If the device overheats, hardware often throttles down the chip's performance to prevent damage and resulting in lower frame rates. And this results in degraded user experience. By keeping the thermals lower with Vulkan, the chip is less likely to throttle, allowing it to maintain higher, stable performance for longer periods. And this ensures like a smoother and longer-lasting experience for the player, particularly in extended gaming sessions like you can expect in such a competitive multiplayer game. The GPU resident drawer is an exciting new optimization that automates the use of the BRG API directly with game objects without needing to implement it yourself with dots. So you save a lot of time on this. The system will automatically and efficiently batch and instance the high-level drawing commands generated by your project's mesh renderer, and this means fewer manual steps for developers with more efficient draw call handling in the background. The commands are processed using the batch render group API, benefiting from features like burst jobified execution and persistent GPU buffers, which reduce the CPU overhead and improve performance like we have seen earlier. The GPU resident drawer works across all platforms except for OpenGLES and WebGL2, meaning it's widely usable on most modern platforms. The GPU resident drawer can provide significant CPU performance gains, especially for complex environments with high instancing potential. Here we see how the GPU resident drawer reduces the draw calls by over 50% in the demo of Fantasy Kingdom in Unity 6. You can also check out the demo on the expo floor on both an iPhone and an Android phone, and you should really check it out, how smooth it runs. Now I hand it over.
Right. Thank you, Oliver. Next up, we'll discuss some optimizations to GPU performance. In this case, we see that we spend around 4 milliseconds every frame waiting for the GPU to finish rendering and presenting previous frames before we can begin processing new ones. And if we can reduce the GPU latency, we'll increase our frame rate. To help with this, we introduced a bunch of optimization tools in the editor. The VFX graph profiling tool gives you feedback on the GPU overhead of your particle systems and effects, so you can optimize them more easily. And we also introduced the shader graph heat map, which gives you information on the rough estimated cost of specific shader graph nodes compared to others. So you can use this to optimize your shader programs. We also recommend you use RenderDoc, which is integrated with the editor, so you can very easily capture frames and perform frame debugging. So you can see how the frame is composed. You can inspect the native graphics commands, draw calls, graphics resources, and identify the associated content and assets and optimize those. And you can also use hardware GPU profilers to get more accurate GPU timing on the device. This is an example from NVIDIA Nsight, and we see on the top, volumetric lighting is taking a very long time, almost 17 milliseconds. So we went to the volumetric settings for HDRP, set the fog control mode to balanced, in this case reducing it down to only 2 milliseconds. When we're GPU bound, we'll often be pixel bound, and there are quick ways to validate this. We can just reduce the rendering and texture resolution and use more simplified replacement shaders. If doing those things suddenly increases your frame rate, then you are pixel bound. And to reduce the pixel overhead, there's a few quick things we can do, but the common cause for pixel overhead is overdraw, which is roughly the amount of times we shade pixels compared to the amount of output pixels. And we can use the rendering debuggers, overdraw visualization on the left, to track the overdraw of different parts of our scene and optimize those with most overdraw. Now, to actually reduce overdraw, we also recommend enabling depth pre-pass or depth priming. You can find it in the rendering settings, which will pre-render the scene to the depth buffer before executing subsequent passes. And this allows us to maximize the benefits of early depth testing, so we can avoid shading occluded pixels. Another interesting note is transparency. Transparent materials generally do not write to the depth buffer to be able to render correctly. This means a lot of overdraw. So if you have a lot of overdraw, you should check your transparency and try to minimize it if possible. But another very common cause for GPU performance bottlenecks, especially on mobile, is memory bandwidth usage. External bandwidth usage increases energy consumption, battery usage, and generates a lot of heat. And of course, mobile devices do not have active cooling, usually, so to avoid overheating, the system will downclock the GPU, which of course limits our performance. And we can either strap a giant block of ice to our phone, or we can try to reduce bandwidth usage. And a common cause for high bandwidth usage is reading and writing to the frame buffer, because we have to transfer a lot of pixel data from the GPU to system memory and back for each render pass. And this is exacerbated by having multiple render targets, rendering at high resolution, and again, having a lot of render passes. With Unity 6, you can use the render graph viewer tool. We really recommend you do that to check all the passes that we create based on the effects you enable and the settings, and all the frame resources and how they are used across passes, as well as the read and write operations with the red and green highlights. But to minimize this overhead, render graph will also track the dependencies of passes and merge compatible passes whenever possible into what we call native render passes. So that is on Vulkan for Android, Metal for Apple Silicon, and DX12 for Windows on ARM. If we look at the example on the right, on the top, example on the left on the top, we see that the G-buffer, deferred lighting, and forward passes are all merged together, as noted by this blue underline under the pass names. And we also see that the G-buffer textures are all loaded from on-tile memory. We see we have this F icon for each of those. This basically enables on-tile deferred rendering. And measuring the 3D sample project, we see a reduction of around 30% in writes from the GPU to system memory. And of course, this allows us to do deferred rendering much more efficiently on mobile. If we test a budget Android device with a 3D sample project, we see that with Forward Plus, we only reach an average 25 FPS. But with on-tile deferred, we very easily reach 30 frames per second for the same content. So we can render more complex content with additional light sources much more efficiently. I'll hand it back to Oliver.
Thanks. As Damian said, render graph merges the passes on the mobile processor and only uses the G-buffer texture on tile without reading from and writing to memory. And here in this sample, we compared built-in deferred to URP deferred. And we measured this on an iPhone 14 Pro, and we saved 60% bandwidth usage. And this is a huge difference that you can also see in the timeline view in Xcode here. So like basically on an Xcode in URP, there's nothing happening on the memory. And on built-in, it's like writing and reading like a lot on chip. And as Damian said, this is like producing heat, like a lot of these devices, so the device will throttle down at some point. There's also a talk about going from built-in to SRP tomorrow at 11. And there we will present this test project in detail, compare the scalability between built-in and SRPs. And we also have like a live in-editor demo of the game Harold Halibut in this session. So you should really check it out. Let's now talk about GPU optimization for pixel processing. Let's focus on two key features, like the new spatial temporal post-processing, or STP for short, and hardware dynamic resolution. STP is Unity's own software-based cross-platform upscaler, and it allows applications to render the intermediate frame buffers as a lower resolution in order to improve GPU performance. And while we're doing that, we maintain near-native visual fidelity. STP is highly versatile. It works on all compute-enabled devices across platforms, and whether you are using URP or HDRP, STP delivers consistent, high-quality results and using advanced spatial and temporal techniques. In our testing, STP has shown a low performance overhead compared to existing upscalers. STP can significantly reduce the time for complex effects like screen-spaced ambient occlusion. You can see here how the benefit offsets the cost of the upscaler. So this is basically the STP cost, and this is like the SSAO path, and it's greatly reduced because of the reduced size. And this means you can use richer post-processing effects, for example, on high-end mobile devices. And it also gets you temporal anti-aliasing with it. On mobile screens, you typically have a high pixel density. And STP can here greatly improve the GPU performance by rendering just less pixels. And again, check out the demo at our booth. It's running on iPhone and Android there. And see if you like the visual quality. There we have like STP reduced by 50%, so it's running at just a quarter of the resolution. Hardware dynamic resolution dynamically adjusts the render area based on the GPU workload, allowing us to scale the resolution while maintaining performance. On platforms like DirectX 12, Vulkan, and Metal, we leverage memory aliasing. This provides faster render target clears and improves performance, all without requiring any shader changes. To preserve visual fidelity, we have a collection of upscaling filters. Each of these upscaling techniques ensures that the final image quality remains high, even when rendering at a lower resolution. Temporal upscaling filters are currently not supported for dynamic resolution on URP, but are integrated in HDRP. Vulkan dynamic resolution was also utilized by Megacity Metro Demo on mobile. It allows us to automatically scale the application's performance across a wide range of mobile devices and GPUs. The GPU workload will vary between frames and across devices and thermal states. With dynamic resolution, we can adaptively scale the render resolution in order to always maintain a smooth frame rate. On the right, we can see the impact of adjusting the render scale on our application's overall frame rate. Vulkan's dynamic resolution integrates seamlessly with the Android Adaptive Performance Framework, which is automatically adjusting the resolution based on the device's thermal states. You can find this tool directly in the package manager. Just type in ADPF, I guess, and then you will find it. It prevents overheating and maintains consistent performance. On this chart, we see the results again in the Megacity Metro demo running with Vulkan dynamic resolution on a Samsung Galaxy S22. The red line shows the baseline full resolution case. And then we reduce the scale to see the improved frame rate and thermal states and see how the line is lowered with each resolution state. Although we don't dive deeply into it, another important feature to mention here is mipmap streaming. This optimization dynamically loads lower or higher resolution mipmaps of textures based on camera distance and screen space. It improves pixel processing by reducing memory usage and improving the texture sampling efficiency. But now let's introduce a new feature into Unity 6, which is foveated rendering for XR. This technique improves the performance by rendering only the central area of the screen in higher detail, while reducing the quality in the peripheral regions where the player's focus is naturally lower. This can significantly boost performance. In Unity 6, foveated rendering is applied to intermediate render passes in URP. On Quest 2 and 3, we use fixed foveated rendering. This reduces the shading rate in a static pattern around the viewer's vision. On Quest Pro, we go a step further with gazed foveated rendering. utilizing the device's eye-tracking hardware, and this allows the foveated area to dynamically adjust based on where the user is looking at. The benchmarks shown here are measured with the URP 3D sample cockpit scene on Quest 2. And you can see how the foveation level greatly improves the GPU time by reducing the overall workload. Application space warp is an advanced XR rendering technique that reduces the rendering frequency while maintaining the display's refresh rate. And this is now also available in URP and Unity 6. The technique works by rendering the scene at half the rate of the XR display. For example, if you want to reach 72 FPS, your app just needs to run in 36 FPS. And then the XR compositor is interpolating the missing frames. To fill in the gaps between the frames, the motion vectors are generated and used to synthesize the missing frames, creating smooth motion even at the reduced rendering frequency. Now let's shift the focus to geometry processing. Geometry processing refers to the stage where 3D models are processed and prepared for rendering on the GPU. Geometry processing is a common bottleneck for GPU performance. In this example on the left, non-pixel processing is the most dominant on the GPU. Vertex on compute work was pending for a large share of GPU cycles. And on the right, we also see poor GPU parallelism and lower shader core utilization. Let's look at the geometry processing stage within the overall graphics pipeline. This is where the vertex data is transformed and prepared for rasterization. A key point to note is that vertex processing does not scale with render resolution. So no matter the resolution, the number of vertices processed remains the same, which means this part of the pipeline can become a bottleneck as the scene complexity increases. And while techniques like frostum culling, which removes objects outside the camera's view, and depth rejection, which skips pixels hidden by others, helps reduce GPU overhead, these processes occur after vertex shading. And this means that the GPU still has to handle the vertex processing before these optimizations take effect. As mentioned by Damian, in RenderDoc, you can already also analyze the draw calls and GPU resource usage. You can pinpoint the most expensive draw calls in your scene, and these are the draw calls that are consuming the most GPU time or resources. RenderDoc allows you to examine the associated content, such as textures, shaders, or other GPU resources, giving you deeper insight into what might be causing the bottleneck. Like this tree here could be like a candidate for optimization. Now let's talk about more mechanisms to improve the geometry processing, like GPU occlusion culling. One of the key ways we optimize draw calls is through indirect draw calls. These allow the GPU to handle the draw parameters directly using compute shaders to define which objects are to be drawn without needing CPU intervention. That makes it faster and more efficient to manage large number of objects in a scene. In addition to indirect draws, GPU occlusion culling ensures that objects hidden by others in the scene are not rendered. And this reduces unnecessary vertex processing and prevents the GPU from wasting resources on pixels that will ultimately be depth culled, and meaning they won't be visible in the final frame anyhow. By skipping occluded objects, we reduce the vertex processing workload, which is particularly important in complex environments with many overlapping objects. In this example, where the rock is in front of many smaller objects, we reduce the vertices significantly with GPU occlusion culling. It is important to note that if you are not bound by these vertices, you would not win any extra performance because it's also adding an extra visibility buffer. One of the significant sources of rendering overhead comes from shadow mapping, which requires the scene to be rendered multiple times, once per light view. And this is especially taxing in scenes with many dynamic lights or a large amount of shadow casting objects. To understand the implications on your scene, you can use the rendering debugger to identify which instances are visible per camera and light view. And this tool helps you pinpoint specific objects or areas that are contributing to shadow mapping overhead, allowing you to optimize your scene for better performance by reducing unnecessary shadow rendering. In HDRP, we have several techniques to help reduce the performance cost of shadow mapping. Dynamic scaled shadows adjust the resolution of the shadow map based on the area on the screen affected by the light. If a light only impacts a small portion on the screen, the shadow map resolution can be scaled down. Another key optimization is shadow map caching. By controlling when shadow maps are updated, we can reduce the rendering overhead. Now we will hand it over back to Damian.
Thank you, Oliver. Next up, we'll discuss about character rendering performance using skinned mesh renderers. This example here on the top, we're basically rendering around 30 animated character models, specifically the Adam model, which is fairly dense in terms of the amount of vertices. And we see that transforming all the vertices on the CPU takes a very long time, almost 80 milliseconds, which is, of course, way too much. But of course, we have GPU skinning, which we supported for quite a while, which allows to offload all these transformations to the GPU using compute shaders. So we perform all these vertex transformations in parallel. And in this case, we reduce the skinning latency to only 1 millisecond. But we can still improve things. If we look at how GPU skinning works, there's actually a lot of inefficiencies. For every blend shape and skinned mesh render that we have, we'll create an additional compute shader dispatch. And we'll also insert GPU barriers between those dispatches to synchronize the GPU. So all of those basically execute in a serialized fashion. The more blend shapes and skin mesh renders we have, the more GPU-GPU synchronization we will have, increasing our overhead and reducing performance. To address this, we introduced an optimization called batched compute skinning, basically a mode for skinning, which consolidates the compute shader dispatches as much as possible based on the resource binding limits on the device. And this way, we end up with a lot less compute dispatches, larger dispatches, with less GPU barriers in between, less GPU to GPU synchronization. So increase our GPU utilization and improve our performance. And the more blend shapes and skin mesh renders and vertices that we have, the more relative performance gains we will see from this mode. And this is supported on all platforms. In the case of this example test, by enabling batch GPU skinning, we reduced the skinning latency by a further 80%. So only ended up at 0.2 milliseconds, which is much better. And lastly, for today, we'll discuss a little bit about ray tracing, optimizations to ray tracing performance, which of course can be quite expensive. First, to be able to do fancy ray tracing, we first need to populate what we call the acceleration structure. We usually call it the RTAS, which describes our scene's geometry. So we add all of our visible instances and procedural geometry to the RTAS. We build it, at which point we can traverse it on the GPU using ray generation shaders. And on intersection, we can then invoke a hit shader to do, for example, lighting calculations, or alternatively invoke a mist shader, so we can shade the sky or background, for example. But for every instance or object that we add to the acceleration structure, we increase the CPU overhead. So I'm having to process the acceleration structure every frame. This example is from a game project. We see that we spend around 9.5 milliseconds every frame processing the acceleration structure, which of course is way too much. To minimize this overhead, we introduced a thing called solid angle calling, which is fairly simple. We just calculate the angle between the instance to camera vector and the instance radius. And if it's below a certain angle threshold, we just discard the instance. So we avoid ray tracing instances or objects that are too small or distant. And you can set it very easily, either through the ray tracing API or through the volume settings for HDRP. If we're testing the 3D sample project, just by setting the solid angle, the calling angle to 4 degrees, we basically eliminate around 85% of ray tracing instances, while still maintaining the same quality pretty much. And if we're testing an actual game project, for example, Den of Wolves by 10 Chambers, by enabling solid angle calling at 4 degrees, we reduce the acceleration structure processing time on the CPU by around 60%. That's a pretty big win. And lastly for today, just discussing optimizations to memory usage. Ray tracing can, of course, use a lot of memory, and we want to do whatever we can to reduce this. We can now use the frame debugger and track the acceleration structure size in memory for every ray tracing shader dispatch. So we can go through our dispatches and track more easily how much memory we're using by enabling ray tracing. And to actually reduce this overhead, we introduced a bunch of optimizations. The first one is blast compaction, which reduces the memory usage for static meshes. Here I'm referring to meshes that don't update their geometry data every frame. They can still transform, of course. We also have a custom GPU memory allocator for small blasts, which reduces the memory usage for small meshes in detail. By blasts, we mean bottom-level acceleration structures, so it's basically the instance geometry. And we also introduced the acceleration structure bill flags. So you can choose between a fast trace and a fast bill flag, and we usually use fast trace by default, except for dynamic meshes. But we also added the minimize memory flag, which you can combine with both, which will just, as the name suggests, reduce memory usage. And in this case, we tested these optimizations using a somewhat large environment, around 6.7 million triangles. At baseline, we saw around 450 megabytes used for the RTAS. By enabling blast compaction and the blast allocator, we reduced this down to 150 megabytes, and then further down to only 100 or so megabytes with the minimized memory flag. So it's a pretty large difference. And just to benefit from this, it's very simple. We just need to check the mesh render settings. Make sure your static geometry is set to either static or dynamic transform in the ray tracing mode, not dynamic geometry. And also enable the minimize memory flag. And I think that's it for today. I think next up we have Q&A. Thank you.
Yep.